All right, hello. Welcome to our review of trigonometry. I'm going to focus just on the basics of sine, cos, tan, which if you don't remember, they apply mostly to right triangles. So we're going to practice sine, cos, tan, review it with right triangles. If you are planning to go into MBA draft, then you can skip this lesson, right? You probably won't need this trig when you get to the MBA. So um, just make sure you send your Algebra 2 teacher a few dollars once you sign your first big contract. All right, so before we get too far in the lesson, just wanted to review quick. If you have like a fraction equals a fraction, it's called like a proportion. Um, you can solve it with cross products, and it kind of has to do with, as weird as it seems, if you take the fraction 1/2 and set it equal to like another fraction that's equivalent to it, 3/6 or something like that, then the numbers across from each other always multiply to the same value. So like 1 times 6 equals 2 times 3, right? And that's true of any fractions that are equal. So if we do 4/10 and 2/5 or something, if you look at the cross products, 4 times 5 is 20, 2 times 10 is also 20. So you can use that fact to solve for x when you have a proportion. All right, so pause the video, try these before continuing. Okay, so how it works is you just take 1 times x, which is just x, and set it equal to 3 times 0.32. Okay, and then you get your answer for x, which would be 0.96. Okay, and then it gets a little bit goofier with x on the bottom here, but I'm going to multiply this so I get 0.5x equals 1 times 8, which is just 8, right? And then I'm going to divide both sides by 0.5 to solve for x. And so we get x equals 16. Okay, and that's called cross products, which we'll end up using in this lesson a little bit. All right, so let's get into it. So the sine, cos, tan, their most basic use is for a right triangle. Okay, and how they work is you have a reference angle, which they're going to call theta or A or something like that. So I'm just going to label in this picture, maybe A is the theta. So this is some degrees, like you could say this is 40 degrees or something like that. And what you do is for each angle here, there's known ratios. Okay, so like let's say that this angle happened to be 40 degrees. All right, so if we were to do then the sine for 40, right? If we were to type sine 40, we'll do it on our calculator here in a second. What that is really telling us is the ratio between, it doesn't tell us anything about the length, but it'll tell us the ratio between this side, the opposite side, and the hypotenuse, right? Sine is the ratio of opposite to hypotenuse. So when you type sine 40, it's going to give you that number. So I'm going to type sine 40 on my calculator. All right, and when you do this, you want to make sure you're in degree mode, right? Because there's you can measure angles in actually both radians and degrees. So if I go into mode here and look, I'm in degree mode. So make sure your calculator is set to that degree mode, not radian, right? And you could tell if you get when you do sine 40, should get this number 0.64. Okay, so what that really tells us is I'm going to write it as a ratio here. So that's really like 0.64 over 1. And what that tells us is this top number is opposite, right? The ratio is opposite to hypotenuse. So basically tells us for every 0.6 units we have here in the opposite, we'll have 1 unit in the hypotenuse. Okay, and so how we sort of use this is if we were to know, say, let's say the hypotenuse was like, I don't know, 10. Let's make it really simple. It was 10. Well, we know that the ratio is for every 1 unit we have here, there's 0.64 over here. So this is where you can kind of do the cross product thing and say, okay, we know the ratio of opposite to hypotenuse is 0.64 to 1. So now if I have 10 in my hypotenuse, I can say, okay, what would that be in the opposite? Put x there, and then you can just solve this with cross products. So you do 1 times x is x, and then 10 times 0.64 is 6.4. So that would tell us that if the hypotenuse was 10, this would be 6.4 units. Okay, and so kind of the idea is that when you type sine 40, that ratio is consistent no matter how big your triangle is, right? If this angle is 40 degrees, then it's always 0.64 to 1, right? So we could say, let's say maybe then the hypotenuse was now 20, right? Then we could do the kind of the same setup and we just have 20 here instead. Okay, and then this would again be double, right? So we could solve this or whatever, but basically when this was 10, it was 0.64. So if this is 20, now we just double this, and this would be 12.8. Okay, because that would keep the ratio consistent, right? And that's true for any 40-degree angle, right? And then all that happens is like that's the ratio again of opposite to hypotenuse. Okay, so it'll change based on the number of degrees. Okay, so I'm going to kind of erase a bunch of this and just show you what I mean by that. So we used, in this previous example, I used A as theta, but we could certainly imagine that this one would be theta. Okay, and so let's say this one was 40, so then this one would be a 50-degree angle. And so now if we look from this angle's perspective, this would now be the op side, and this would, the hypotenuse would be the same, I guess. But the ratio is going to be different, right? If you look, this side, this op side is longer than the one that was over here. Okay, so for the 50-degree angle, there's a different ratio, right? So when you type sine 50 on your calculator, that's going to give you a different ratio of op to hypotenuse because the angle is different now, right? The side is now bigger because we have a bigger angle here. Okay, so if I type sine 50, all right, that gives us point, I'm going to call it 0.77 just to round it. But basically that means for a 50-degree angle, for every 1 unit that's in the hypotenuse, we have 0.77 units in opposite. Okay, and then again, if we knew one of these, right, if we happen to know either the opposite or hypotenuse, let's say the opposite was 12 units long, then we could set it up where we could put the op on the top, hypotenuse as x, right, and then solve that to figure out what x is. Okay, so that's kind of a review of them. And there's 3 different ratios. So the sine one, which they call SO, is a ratio between the opposite and hypotenuse sides. Ca for cosine is a ratio of adjacent over hypotenuse. All right, and so this angle, right, its cosine ratio would be this side here and this side here, right? It'd be adjacent to hypotenuse, right? So we could do the cosine for 50 degrees. We just have to use 2 different sides. Okay, and then the last one is called tan, which is TOA. If you remember SOHCAHTOA, and tan is the ratio between opposite and adjacent. Okay, and in school when I learned this, all I ever did was like type them in and get these decimals, but I never really knew what they meant. And they really mean ratio between different pairs of sides, right? And there's, for each sine, cos, tan, there's a different pair that's in your ratio. Okay, so like the one thing that I think might help here is just the idea that like the sine function just takes in an angle measure and returns a known ratio. Okay, so you can look at for sine, as the angle gets bigger, the ratio of, remember sine is op to hypotenuse, that ratio gets closer and closer to 1, which kind of makes sense. If you have an 80-degree angle, right, I'll try to draw an 80-degree angle here. It's not the greatest, but at this point, the opposite is getting pretty close to the hypotenuse. It's almost 1 to 1, right? As you get really big, op and hypotenuse almost become the same, and that's what this ratio is saying. Okay, so all the when you do sine of an angle, all it is giving you a known ratio. Okay, so let's actually get to some sample problems here. There's steps here, but honestly, you know, hopefully they'll make sense as we do the practice questions. All right, so kind of like the first step in this process is we've got to figure out which ratio to use. Okay, and we'll set up a proportion, use our calculator, and then solve it from there. Okay, so in this one we've got angle A is 30 degrees. Okay, and so we have, if we look at our sides, right, so from this angle's perspective, this is the side opposite, this is the side adjacent, okay, and this one is our hypotenuse. Okay, and so the 2 sides that are labeled are this x and 12, and that's op and hypotenuse. So that would be sine is op and hypotenuse. So what we would do for our setup is we would say sine of 30 degrees equals op x over hypotenuse 12. Okay, and then what we're going to do is we're going to turn this side into a ratio, right? So I'm going to type sine of 30 degrees right? And that turns out to be 0.5. Okay, so that really says if the angle is 30 degrees, our ratio is 0.5 to 1. That's the ratio of op. Remember, sine is op over hypotenuse. So for every half there is in the opposite side, there's 1 in the hypotenuse. So now just use our setup, right? So we have 12 in the hypotenuse and we don't know what's in the op. So we can just set it up, and basically you could do this mentally, right? If the ratio is 0.5 to 1, it should be 6. Um, or you can do cross products. So do 0.5 times 12 and 1 times x is just x. So any way you do it here, that'll figure out that this side is 6. Okay. Let's try one more like this. All right, so I would label the side and figure out is this a sine, cos, or tan problem. All right, so from this angle's perspective, this side would be opposite leg, and this would be the adjacent leg. Okay, and our hypotenuse is always the long side, but we're not using it here. We have op and adjacent. So op adjacent is TOA. So this is a tan problem. Okay, so our setup would be the tan for ratio for 59 degrees has to equal our ratio, which is op of h over op over adjacent, which is 45. Okay, and again, now I'm just going to turn this into a ratio on my calculator. So I'm going to type tan of 59. All right, which is 1.66, I guess. So we have 1.66 to 1. So it looks like the op is bigger than the adjacent, which visually makes sense. Okay, and now I just got to solve this with my cross products. So 1 times h is just h, and 45 times 1.66. So I'm just going to take it times my previous answer times 45. So that's about 74.9. Okay, and that fills in our missing side here, which makes sense, right? If this side is 45, it makes sense that this one's decently bigger than it. All right, one more basic one, right? Start with is it sine, cos, tan, and then go from there. Pause the video, give it a shot. I guess I should say this should be a right angle too, right? This won't work unless the triangle's a right triangle. So I should have had that in here. Anyways, here's our reference angle. So from that angle's perspective, this leg is adjacent and this is hypotenuse. Okay, so what we can do is then say we're going to use cosine, because cosine is adjacent and hypotenuse. All right, so I'm going to write the cosine for 30 degrees has to be equal to our ratio, which is adjacent 76, right? It's always adjacent over hypotenuse. So 76 over the missing side d. Okay, and I'm going to do cos 30 on my calculator. All right, so 0.87. So I get 0.87 to 1 equals 76 over d. Now I'll solve this with cross products again. So 0.87 times d equals 1 times 76. Now I'm going to divide both sides by 0.87. So d is going to equal to 76 divided by that number. So I'm going to do 76 divided by my previous answer. All right, and so I get about 87.8. Okay, and that would be the length of the missing side here, the missing hypotenuse, which makes sense, it's longer than the leg, right? Because hypotenuse should always be the longest side.